Hello, and welcome to Think Around Space, the podcast where we explore the wonders of the cosmos and uncover the mysteries that lie beyond our world. I'm your host, and today we're going on a journey to what might just be the loneliest place in the entire universe. Imagine a region of space so vast and empty that if our Milky Way galaxy were located there, we wouldn't have known other galaxies existed until the 1960s. A cosmic desert where darkness reigns supreme, and the usual tapestry of galaxies is replaced by, well, almost nothing at all. This isn't science fiction, it's real, and it's called the Boötes Void. This mysterious structure, discovered entirely by accident, stretches across an incomprehensible 330 million light-years of space, yet contains only a handful of galaxies where thousands should be. Today, we'll explore this cosmic enigma, how it was found, what it teaches us about our universe, and why it continues to capture our imagination like few other celestial phenomena. So let's dive into the great nothing and discover what the darkest patches of our cosmos can reveal about the very nature of reality itself. So what exactly is this Boötes Void we're talking about? Picture this. A spherical region of space about 700 million light-years from Earth in the direction of the constellation Boötes, hence its name. This void spans an incredible 330 million light-years across. To put that in perspective, it's about 0.3% of the diameter of our entire observable universe. But here's where it gets really mind-bending. In a volume that large, astronomers would normally expect to find around 2,000 galaxies based on average cosmic density. Instead, the Boötes Void contains only about 60 galaxies. That's just 3% of what should be there. It's as if someone took a cosmic spoon and scooped out a massive section of the universe, leaving behind only the barest remnants. If our Milky Way were at the center of this void, nearly our entire night sky would be black. No neighboring galaxies like Andromeda visible to the naked eye. No distant galactic clusters dotting the cosmic horizon. Just the stars within our own galaxy, and then this vast, profound emptiness. As one astronomer poetically noted, if we had evolved in the Boötes Void, we wouldn't have known there were other galaxies until we developed the technology to detect them in the 1960s. The few galaxies that do exist within this void aren't even spread evenly throughout. They're arranged in a sort of tube or thread running through the void's center, as if a thin filament of the cosmic web managed to snake its way across the emptiness. This strange distribution only adds to the mystery of this cosmic anomaly. The discovery of this enormous void came completely by surprise in 1981. Astronomer Robert Kirshner and his colleagues at the University of Michigan weren't looking for voids at all. They were conducting a pioneering redshift survey, measuring distances to galaxies to create a three-dimensional map of how galaxies are distributed in space. As their map took shape, something bizarre appeared. In 3 of their survey fields, separated by about 35 degrees on the sky, they noticed an enormous gap in galaxy redshifts. A huge volume of space with virtually no galaxies detected. At first, such a blank spot seemed too dramatic to be true. The astronomers double-checked their data, calibrated their instruments, and ran their numbers again, suspecting some kind of error. But the emptiness was real and persistent. Kirshner informally dubbed it the Great Nothing, a name that perfectly captured the shock of finding such a vast cosmic hole. Later, as news spread through the astronomical community, it took on the more formal name Boötes Void because of its location in the sky.
When Kirshner and his collaborators formally announced their discovery in the mid-1980s, they described a void roughly 50 megaparsecs in size, about 160 million light-years initially, though later observations expanded this to about 100 megaparsecs, or 330 million light-years. They noted that the Boötes Void's extremely low galaxy density was of high statistical significance, far beyond what could be explained by random chance.
This discovery was revolutionary. Along with other voids and superclusters found around the same time, it helped overturn the long-held belief that the universe, on large scales, should be relatively uniform. Instead, it revealed a cosmos more like foam or Swiss cheese, a cosmic web of filaments and walls with enormous voids between them.
There's something psychologically unsettling about the Boötes Void that goes beyond mere scientific curiosity. It challenges our expectation of a somewhat evenly distributed universe and confronts us with emptiness on a scale that's difficult to comprehend. Think about it. We're used to seeing images of space filled with galaxies, nebulae, and stars. Even the empty spaces between galaxies contain dust, gas, and radiation. But the Boötes Void is different. It's mostly truly nothing, observable only by the absence of galaxies where there should be thousands.
This extreme isolation runs counter to how we normally think about the cosmos. Galaxies are naturally social. They tend to cluster and form groups, interacting and merging over billions of years. But inside the Boötes Void, there's no cosmic dance, no galactic neighborhood, just occasional lonely galaxies floating in profound isolation.
It's no wonder that the Boötes Void has been called the loneliest place in the universe. If you were adrift in its center, you would see almost no galaxies in any direction, just darkness punctured by the faint glow of a few far-off realms. The psychological impact of such cosmic desolation is hard to overstate. It reminds us that despite the incredible richness of our cosmic neighborhood, the universe as a whole is dominated by vast expanses of emptiness.
In sky surveys, when astronomers map galaxy positions, the Boötes Void shows up as a conspicuous circular zone with hardly any dots, ringed by denser regions. All the stars we might see inside that marked circle are actually foreground objects from our own Milky Way. Virtually nothing exists inside at the void's distance.
So how do such enormous voids form in the first place? The answer lies in the early universe and the power of gravity over billions of years. Modern cosmology tells us that the early universe was a hot, dense soup of matter and radiation that was remarkably uniform, with only tiny irregularities, random quantum fluctuations, causing slight differences in density from place to place. These differences were minuscule, perhaps just 1 part in 100,000, but they were the seeds of everything we see today.
As the universe expanded after the Big Bang, gravity began to amplify these small density differences. Regions that were slightly denser exerted a stronger gravitational pull, drawing in more matter from their surroundings. Meanwhile, the less dense regions lost matter to the denser ones, becoming even more empty.
This process is like a cosmic version of the rich get richer effect. Matter flows into the denser clumps, leaving behind expanding voids that become ever more underpopulated. Over billions of years, the matter in the universe condensed into a filamentary network, what we now call the cosmic web, with long filaments and sheet-like walls of galaxies and galaxy clusters, with huge voids between them.
Think of it like soap suds or foam. As bubbles form and stick together, empty spaces are enclosed by the soap film. The voids are like the bubbles inside this foam, and the galaxies lie on the thin walls and strands surrounding them. The Boötes Void likely formed like any other void, but perhaps through an especially fortuitous merging of smaller voids. As time goes on, smaller voids can coalesce into larger ones, just as small soap bubbles merge to form a big bubble. If several adjacent low-density regions in the early universe happen to line up and join, they'd create one supervoid. It's hypothesized that the Boötes Void is exactly this, the result of void mergers, which would also explain why it isn't completely empty. The 60 galaxies in that tube might mark where the edges of the original smaller voids met and left a thread of galaxies behind in the middle. Crucially, the formation of the Boötes Void doesn't require any exotic new physics. It's simply an exaggerated example of the normal process of cosmic structure formation. Computer simulations of the universe routinely show voids developing and growing as matter congregates into filaments and clusters. Most voids are smaller, but occasionally simulations produce a really large void when several align. Beyond its sheer wow factor, why do astronomers care so much about the Boötes Void and cosmic voids in general? It turns out that studying these gigantic emptinesses yields valuable insights into some of the biggest questions in cosmology. First, voids serve as crucial tests for our cosmological models. The properties of voids, their sizes, shapes, and how common they are sensitive indicators of whether our understanding of the universe is correct. A successful model of the universe must be able to produce voids like Boötes in computer simulations. Early on, the Boötes Void was somewhat challenging to explain, but now it's considered a good confirmation that our current cosmological models are on the right track. Second, voids are especially sensitive to the effects of dark energy, the mysterious force accelerating the universe's expansion. Because voids are underdense, their expansion can be slightly different from that of denser regions. By measuring void profiles and comparing them to theoretical predictions, scientists can test how dark energy has influenced structure formation over time. Third, the few galaxies inside the Boötes Void are like laboratories for studying galaxy evolution in extreme isolation. Since they have few neighbors, they likely evolve differently compared to galaxies in clusters. Observations show void galaxies tend to be smaller and have higher specific star formation rates. They keep making new stars slowly over time, unlike galaxies in crowded regions that often exhaust their gas more quickly. Fourth, and perhaps most surprisingly, voids can help us study neutrinos, those nearly massless subatomic particles that are abundant from the Big Bang. Neutrinos' tiny masses influence how structure forms, and voids amplify their effects because they're low-density regions. By studying void characteristics, astronomers can place constraints on neutrino properties. The discovery of the Boötes Void also helped kickstart more ambitious redshift surveys. Today, projects like the Dark Energy Survey and Sloan Digital Sky Survey have mapped millions of galaxies, revealing a beautiful 3D map of the universe with a clear web-like structure. Is the Boötes Void truly unique? It's exceptional, but it's not the only large void out there. As astronomers expanded their galaxy maps in the decades after 1981, they found many other voids peppered throughout the cosmos, confirming that voids and filaments are the cosmic norm. Our own Milky Way is near the edge of an underdense region called the local void, also nicknamed the KBC void after researchers who identified it. This void is estimated to be roughly 1 to 2 billion light-years across, though its exact size and emptiness are still debated. If true, that would make our local underdensity even larger than Boötes Void in size, though it's not as completely empty. In 1988, astronomers reported a giant void in the northern galactic hemisphere, about 300 to 400 megaparsecs in diameter. That's on the order of 1 billion plus light-years across,
substantially larger than Boötes, though much farther away.
More recently, studies have suggested a huge void in the direction of the constellation Eridanus, coincident with the puzzling cold spot in the cosmic microwave background radiation. This Eridanus supervoid was claimed to be on the order of 500 million to 1 billion plus light-years across, though evidence for this supervoid is contested.
In essence, the cosmic web is a vast network of filaments and voids, and Boötes Void is one particularly large cell in that cosmic foam. It's worth noting that voids can have differing emptiness. Some might have 10 to 20% of the average galaxy density, while others, like Boötes, have only a few percent. But what they all have in common is that voids make up most of the universe's volume, even though they contain relatively little of its matter.
Whenever a phenomenon captures public imagination like the Boötes Void has, it's inevitable that alternative theories and wild ideas spring up to explain it. While mainstream science attributes the void to natural cosmological processes, some have let their imaginations roam free.
One whimsical notion involves alien supercivilizations. Could an incredibly advanced extraterrestrial civilization be responsible for the void? The idea suggests that a Kardashev Type 3 civilization, capable of using the energy of billions of stars, might have dismantled or relocated stars and galaxies in this region for their own purposes. Alternatively, they might have built megastructures like enormous Dyson spheres around every star in the void, absorbing all their light so we cannot see them.
In recent years, with the simulation hypothesis gaining pop culture attention, the Boötes Void has been playfully pointed to as a potential simulation error, essentially a part of the universe that the programmers forgot to fill in. Others have speculated more exotic physics. Perhaps there was some kind of unknown cosmic event or object that cleared out this volume. A supermassive black hole that wandered through and consumed everything? An intersection of parallel universes that canceled matter in that region? There's no evidence for such proposals, but they capture the imagination. It's important to stress that none of these fringe ideas have evidence behind them. The consensus remains that normal cosmology explains the void, but the fact that the Boötes Void sparks such creativity is in itself notable. The Boötes Void remains one of the most captivating cosmic structures we've ever discovered. It represents nature's grand scale of contrast between presence and absence, light and dark, matter and void. In exploring this cosmic enigma, we've journeyed through its basic facts, an immense sphere 330 million light-years wide with only a few dozen galaxies. We've learned about its accidental discovery in 1981 by curious astronomers mapping the universe and the sense of mystery it evoked. We've discovered that while it appeared baffling at first, it can be explained as an extreme outcome of cosmic evolution, a massive bubble in the foamy structure of the universe. We've compared it with other voids, finding that it's a record holder among nearby voids, though even larger voids likely exist in the farther reaches of space. We've discussed why scientists today still study voids like Boötes. To test theories of the cosmos, probe dark energy, wade ghostly neutrinos, and understand how galaxies grow in isolation. In the end, the Boötes Void is both a physical reality and a symbol. As a reality, it's a testament to the richness of the cosmic web, illustrating that the universe's structure includes not just the galaxies we see, but also the enormous voids that we don't. As a symbol, it invites us to contemplate emptiness on an unimaginable scale, perhaps even stirring reflection on existential themes of loneliness and nothingness. The Boötes Void continues to loom in our cosmic maps, a reminder that when we gaze into the universe, sometimes the darkest patches have the most to say. In studying this great nothing, we learn more about everything that surrounds us.
Thanks for joining me on Think Around Space today. If you found this journey into cosmic emptiness fascinating, consider sharing this episode with fellow space enthusiasts. Until next time, keep looking up, even when what you find is nothing at all.